All right, let's discuss chapter 14, which is about central limit theorem. And central limit theorem is the most important theorem in statistics. And it's probably one of the most fascinating things that you will ever learn in your life, because in nature, this idea of observing normal distribution is something very common, right? And central limit theorem gives you an idea why we observe normal distribution a lot, and it is used in statistics a lot. A lot of theorems in statistics, a lot of concepts, and a lot of theorems are based on central limit theorem. So if someone looks at a lot of proofs in statistics, he is going to figure out that many of them come from this theorem, and this might have been used somewhere in those theorems. So the first thing that I need to explain about this is the concept of sampling distribution, okay? When we say sampling distribution, that is different from sample distribution. That is different from distribution of the sample, right? When you have a data, when you have a sample, the data in the sample might have a distribution, right? It has a distribution, and that is a distribution of the sample. That is the distribution of the data that you have. So that is sample distribution, or the distribution of the sample. And when your sample gets larger and larger, the distribution that you see in the sample is going to match the distribution in the population, right? Because the sample is becoming more similar to the population. So in general, we have this concept of sample distribution or distribution in the sample, but that is different from sampling distribution. This terminology is very important, okay? What is sampling distribution? I have already talked about that. When we choose a sample from a population, okay, and you find a proportion in the sample, okay, the sample proportion itself has a distribution, right? If, for example, you want to figure out the percentage of people supporting the Conservative Party of Canada in an election, okay? Now, just assume that 35% of Canadian people support the Conservative Party of Canada, okay? Now you have a sample from the population, a sample of 100 people, okay? Imagine that we are going to have a sample of 100 people from the Canadian population, and in the sample of 100 people, you count the number of people supporting the Conservative Party of Canada, for example, and you find a proportion, right? You divide the number of people, you divide x by n, right, to find the proportion in the sample, right? P hat is the sample proportion. So that is a sample of 100 people that you have from the Canadian population. Now you do this 1,000 times, right? Every time you find a sample, and in the sample you find the sample proportion, right? Number of proportion of people in the sample supporting the Conservative Party of Canada. And imagine that, every time you're choosing 100 people, right, from the population. So the sample size, for example, is 100, okay? And this sample proportion, which is a statistic, it has a distribution. Because as I mentioned, that itself is a random variable. And it depends, the outcome depends on the sample that you have chosen from the population, right? So the distribution of this sample statistic, the distribution of sample proportion, for example, is called sampling distribution of sample proportion. So when we talk about sampling distribution, we talk about distribution of a sample statistic, okay? So if you're talking about, for example, proportion of people supporting something, if we're talking about a categorical variable, and for that we have proportion, we have counts, and we have proportions. In that case, when we talk about sampling distribution, it's usually sampling distribution of the sample proportion, right? P hat is sample proportion. And the terminology used for its distribution is sampling proportion, right? So we choose, for example, 1,000 samples, and in each sample we have 100 people, right? In each sample you find the sample proportion, and now you have 1,000 data points. You can find sampling distribution of sample proportion, okay? Now that is for a categorical variable. And for this, in the previous chapter, we discussed that for the number of success for the number, x can be approximated using this normal model, right? And we had some assumptions for that. And the proportion, the sample proportion, the distribution for that, sampling distribution of sample proportion is approximated by a normal model. We showed in the previous chapter that this normal model, mean for that is p, and the standard deviation for that is the square root of pq over n. What were the conditions? Sample is smaller than 10% of the population, and we have at least 10 failure and 10 success in the sample. That expected number of failure and expected number of success, NP and NQ, both of them are larger than 10. And we have used simple random sample to choose a sample from the population, right? That was for a categorical variable, right? Now imagine that we are talking about height for people in Canada, right? That is a continuous variable. I choose a sample of 100 people from the Canadian population, and I find sample mean for height, okay? I find sample mean, and it's, for example, 180 centimeters. Then I put them back in the population. Again, I choose a sample from the population. I choose a sample of 100 people. This time, I calculate sample mean for height, and it's going to be 179. I do this again and again, and I find so many numbers for sample mean, right? We are talking about height, for example, in Canada. Height is a continuous random variable, right? So in that case, we are talking about sampling distribution of sample mean, right? So we usually, in this course, talk about sampling distribution of sample proportion if you're dealing with categorical variables, or sampling distribution of sample mean if you're talking about quantitative, continuous random variables, right? Like height, weight, and things like that we have discussed a lot before. So we can have sampling distribution of a sample statistic, okay? This sample statistic can be sample mean or can be sample proportion or anything else, okay? But the central limit theorem, as we discussed, is about sample mean, okay? It's a fascinating thing that statisticians have discovered and proved that, that no matter what the distribution in the population is, if your sample is large enough, and if the assumptions of central limit theorem are valid that we will discuss, the sampling distribution of sample mean is going to be well approximated by a normal model. So if we talk about height for people in Canada, it may not be normally distributed, right? It might be skewed to the left, skewed to the right, bimodal, or anything else, right? But when you choose a sample, and if the sample is large enough, and in this course is usually 30, if the sample is large enough, the sample mean has a normal distribution. The assumption that you need for that is the assumption of independence. And for that, what do you need? You need a sample which is less than 10% of the population, and simple random sampling has been used for choosing a sample from the population, okay? And the sample need to be large enough, okay? These are the assumptions. Simple random sample, assumption of independence, so the sample is less than 10% of the population, and the sample needs to be large enough. Okay. This is quite interesting. And this is called central limit theorem. Central here means foundational or fundamental. This is the most fundamental theorem in statistics. That no matter what the distribution in the population is, they have proved that sampling distribution of sample mean can be approximated by a normal model if the sample is large enough. Okay? If the sample is not large, if the sample is small, for example, we have 5 people or 6 people. Imagine that instead of 100 people, every time that I choose a sample from the Canadian population, I choose 5 people, okay? I find the average height, and I do this like 1,000,000 times. 1,000,000 times, I choose 5 people from the Canadian population, and I calculate sample mean, okay? Now that sample mean, if height in Canada, in the population of Canada, is not normally distributed, that is not going to be normally distributed because the sample that I choose every time is just 5 people. N is small. If N is small, what happens, this cannot be approximated by a normal model. If the sample is large enough, which is usually 30 in this course, if it's smaller than 30, we are going to just tell you that the assumptions of central limit theorem are valid. So if the sample is small, that is not valid. It's not going to be, the sampling distribution of the sample mean is not going to be normal, okay? The only way it can be normal if the sample is small is that the population, the variable in the population itself is normally distributed. If height is normally distributed in the Canadian population, okay, and I choose a sample of 5 people, and I do this many times, and I find sampling distribution of sample mean, this is exactly normal. Because height itself in the Canadian population was normally distributed. In that case, you don't need to have a large sample. And using what we have learned so far, you can simply prove that it is normal because you can show that when we talk about summation of some independent normal random variables, the summation is also a normal random variable, and we know how to find the expected value for that using the expected value of the random variables, and how to find the variance or a standard deviation for this summation using the standard deviation of those variables, and we know how to use the independence assumption for that, okay? So if the sample is small, and if height for people in Canada is normally distributed, no matter what the sample size is, sampling distribution of sample mean is going to be normal, okay? But that is not central limit theorem. Central limit theorem says no matter what the distribution of that random variable of height in the population is, it doesn't need to be normal in the population. If your sample is large enough, what happens is that the distribution, the sampling distribution of the sample mean is going to be normal, right? And when we talk about sample proportion, that is just a special case of this, right? Because if we are talking about, for example, binary categorical variables, the outcome is 0 or 1, sample proportion is just sample mean, right? So that is just a special case of this. And this is a more general form of that. And in this book, a very important assumption in using central limit theorem is independence. In some more advanced textbooks, there are theorems that they relax that assumption of independence, and they somehow show that if sample is large, then the sampling distribution, again, is going to be normal. But that is not something that we discuss in this course. In this course, we have these assumptions that I mentioned. Simple random sample, less than 10% of the population, and large enough sample, and the assumption of independence, right? So x, if x is normally distributed, if x, which can be, for example, weight or height in Canada, right? If x is normally distributed, x bar, you can simply prove that using what we have learned so far. X bar, which is sample mean, that is normally distributed as well. And if mean in the population is mu and sigma in the population is sigma, the standard deviation in the population is sigma, then mean for the sample mean is going to be mu, which is the population mean, and standard deviation for the sample mean is going to be the population standard deviation divided by the square root of n, okay? So this is normally distributed. If the parameter in the population is normally distributed, no matter how large n is, right? Now, the central limit theorem says no matter what this distribution is, there are question marks here. Because in general, we don't know the distribution in the population, right? We don't know the distribution in the population. We don't have all the data in the population, right? So central limit theorem says no matter what the distribution in the population is, if your sample is large enough, and if we have the assumptions of central limit theorem, we still have this. We still know that the distribution for sample mean is normal. Okay, the distribution for sample mean is normal if if n is large enough and if the assumptions of central limit theorem are valid, okay, which is very interesting, right? And I talked about this, and you can look at the details. This is just a note of what I just mentioned. You can read this yourself. And by the way, I have put the slides with the notes in on Quarkus for the last two, PowerPoint documents that I have put there. So I thought that I shouldn't spend time on writing things in these two sessions, just to focus on the concepts. I put my notes there as well so that you can have access to them and we can save time a little bit. So this is something that we discussed. Okay, now let's do some examples. First example, a sample of size n25, n is equal to 25, is drawn from a population with mean 40 and a standard deviation 10. What is probability that sample mean will be between 36 and 44? And assume that central limit theorem applies. Okay, so here, population mean is given, it's 40. Population standard deviation is given, it's 10, okay? Now the question is that what is the probability that sample mean, okay, x bar, is between 36 and 44, right? Now, because the assumptions of central limit theorem are valid, we know that x bar, or sample mean, is normally distributed. Mean for that is the population mean, and a standard deviation for that is the population standard deviation divided by the square root of n, okay? So mean is going to be 40, and a standard deviation for x bar is going to be 2, okay? Now, if we go to the next slide, we can easily do this using Z table, right? This is something that we have done before, so I'm not going to spend time on this. You can find the z-score associated with 36, z-score associated to 44, and in the past, we have done this, right? We know that we can find out here that the z-score for 44 is 2, and z-score for 36 is -2, and therefore, we are interested in the probability of z between -2 and 2, right? And if we look at the table, it's going to be 95, 44, right? 0.9544. If we didn't have the table, we could just quickly say it's about 95%, right? Because we know the approximate value. We know that if you're to a standard deviation far from the mean, if you're approximately to a standard deviation far from the mean, the proportion associated with that interval is approximately 95%. But here, we have a more precise value if we use the table for that. And we know how to do that, right? We have done a lot of examples related to that in the midterm. So you need to know the things that we learned for the midterm exam. You need them for the final exam as well. First of all, final exam is cumulative. It's going to cover everything that we have taught. But obviously, the focus is going to be more on the things that we have discussed after the midterm exam. But remember that you still need to be very comfortable working with the concepts that we learned before the midterm exam, right? So, example. Suppose that weights of airline passengers are known to have a distribution with mean of 75 kilograms and a standard deviation of 10 kilograms. A certain plane has a passenger weight capacity of 7,700 kilograms. What is the probability that a flight of 100 passengers will exceed the capacity? Okay. So X, which is weight of airline passengers, the assumption is that that is coming from a population, and we don't know the distribution for that. We just know that mean, the population mean is 75, and population standard deviation is 10, okay? Now, the number of passengers that we have is 100. So the sample that we have is a sample of 100 people, okay? And for the weight to be larger than 7,700, because we have 100 people, sample mean need to be larger than 77, right? So we are interested in the probability of sample mean larger than 77, right? This is what the question is asking. And we know that the assumption, we can assume here that the assumption of central limit theorem, the assumption here is that the assumption of central limit theorems are valid because the sample is large enough, right? And we also assume that it's less than 10% of the population, right? The number of airplane passengers in general is much more than 100 all over the world, right? 100 is less than 10%, right? So we can use the assumption of independence, and at the same time, sample is large enough. So we can use central limit theorem and say X bar is normally distributed. Mean for that is 75, and a standard deviation for that is a standard deviation in the population divided by a square root of n, which is going to be 1 here, right? So we can use the knowledge that we had about normal distribution to find the probability of X bar larger than or equal to 77. You can find the Z score associated with 77 and find, the proportion associated with Z score less than that value. Then 1 minus probability of that is going to be the value that you're interested in, the probability that you're interested in, right? This is something that we have discussed before. Before I start next chapter, I just want to briefly mention something that, as you see in the formulation for central limit theorem, sample mean, first of all, mean for that is the population mean, right? So it's an unbiased estimator of the population, right? Mean for that is equal to the population mean. It's an unbiased estimator of the population parameter, right? Another thing is that the standard deviation for that is smaller than the standard deviation of the population, right? So if you talk about, for example, height for people in Canada, you choose one person, that person might be 160. You choose another person, that might be 190. You choose another person, that might be, for example, 210, right? The spread of the data in the population is more, right? But when we choose sample from the population, and if the sample is large enough, what happens is that when you calculate the sample mean, you have a sample of 100 people, you calculate the sample mean, it's going to be, for example, 179. You choose another sample, 100 people from the Canadian population, the sample mean is going to be, for example, 180. Next time you do that, it's going to be, for example, 179.5, right? You can, in an intuitive way, understand that is going, because that is an average, the variability for that is smaller, right? The spread of the data, when we talk about the data related to sample statistic, right? When we find sample statistics for a statistic for many samples, when we talk about sample mean specifically, the variability of that is going to be less than the variability of the original data in the population, right? You choose people from the population, you measure their heights, and you see that, in the population, there is a large variability. You choose one person, 180, another person, 150, and so on. But when you find a sample of 100 people and you find the sample mean, then you find another sample of 100 people, you find the sample mean. These sample means are closer to each other, right? And you can see that in the formulation that we have for the standard deviation of sample mean, right? When we talk about sampling distribution of sample mean, we see that here the standard deviation is small, especially if n is large. This is going to be much smaller than the standard deviation in the population, right? And that is something that we like, right? Because we want to have a good estimate, right? We don't want to have like a very large standard deviation. In that case, the spread of the data is going to be large. Because when we talk about sample mean or sample proportion, these are called point estimate, okay? It's the best guess that we have about the population using that sample, right? When we have a sample, we calculate the sample statistics. That is a point estimate. It's the best estimate about the population parameter, right? Just using that sample. And you feel better about that if the standard deviation of the distribution associated with that is smaller, because you just feel that, the spread of the data is smaller. So this is probably a good guess. But a better measurement for that is when we discuss about confidence interval, okay? Now, what is a confidence interval? How much time do we have? So the sampling distribution, p hat, right, is approximated using a normal model, and we know what is mean for that and what is the standard deviation for that. And here we are just talking about confidence interval for proportions. In this chapter, we are not talking about confidence interval for sample mean. We are talking about sample proportion, and we are talking about proportion here, and the confidence interval for that. In another chapter, we discuss about confidence interval for mean, and that is quite similar to this. So here we are talking about confidence interval for proportion, right? Now, here's the thing. In reality, we don't have the population proportion, right? We are interested in that. In reality, we don't have the population mean or proportion, right? That is something that we are interested in. So far in the examples that we discussed, we were given the population parameter, right? But in reality, the population parameter is something that we are interested in, right? And we are using the sample statistic as a guess, as a best estimate for that when we have just one sample, right? But what is confidence interval? So first, I'm going to talk about a standard error, okay? So we know a standard deviation for, we know that standard deviation for sample proportion, right? This sample proportion has a normal distribution, and a standard deviation for that is the square root of pq over n, right? But the thing is that we don't have p, we don't have q, right? P and q are coming from the population. We don't have that, right? So in practice, we are not able to find that standard deviation, because this standard deviation for p hat is dependent on p and q in the population, okay? So what's the trick if we want to have an estimate for that? We just using this formulation, pq over n, just the estimate that we have using the sample, right? So we have one sample, and instead of finding that standard deviation, okay, we find something which is called a standard error. A standard error is just an estimate of a standard deviation. Because in the formulation for that, instead of using population parameter, we just use sample statistic, okay? So this is called a standard error of p hat, okay? Now, sampling distribution approximately normal when NP is larger than 10 and NQ is larger than 10, right? We know this, right? But here, again, we don't have P, we don't have Q, right? So we just look at our sample and we calculate NP hat and NQ hat, right? So we calculate NP hat is the number of success in our sample. NQ hat is the number of failure in our sample, right? So this was the formulation for a standard deviation of p hat. This is the exact value for that. But this is something that we call a standard error for p hat. And a standard error for p hat is p hat q hat over n, okay? We just replace p and q by the estimate that we have from our sample. So for every sample, a standard error is different, because that depends on the sample proportion, and sample proportion is different from one sample to another sample, right? So now, let's look at this example. Opinion poll with 1,000 randomly sampled Canadians has been done, and 91% believe Canada's healthcare system is better than the US. Estimate of the proportion of Canadians who believe Canada's healthcare system is better than the US is 91%, right? Because p hat, using the sample that we have, in the sample, 91%, meaning that 910 people out of 1,000 people that we have in the sample, they believe that the Canadian healthcare is better, right? Now, what is a standard error? If the question just says, what is a standard error? This is the standard error. A standard error is the square root of p hat q hat over n. A standard error is just an estimate for the standard deviation of p hat, okay? And sometimes the result is shown like this, 91% or 0.91 plus minus a standard error. So if you see this, this is going to be proportion, okay, and this is going to be a standard error, okay? Sometimes this is used, and this is not confidence interval. This is just to show, if you see something like this, and this is denoted by a standard error, it's just to show that this is the estimate that we have for the population parameter. So this is the sample proportion, and this is the standard error that we have for sample proportion. That's just the meaning of this. This is not an interval, okay? So this is just, if you see something like this, and we usually have, we usually don't say this in like the exam and in the course, because we usually work with the confidence interval, but you know, this is sample proportion, and this is the standard error for estimating the standard deviation of the sample proportion, right? Now, what is confidence interval? This is confidence interval. And I will explain what that means. The formulation is quite simple. And you see confidence interval for sample mean, for sample proportion. You see confidence interval for mean and proportion, right? We are talking about confidence interval for population proportion, not sample proportion. We are interested to see what is the interval in which the population proportion lies, right? We want to find an interval in which the population proportion is, right? So we have confidence interval for population proportion, and we have confidence interval for population mean, right? Now, what is the formulation for that? So far, we know how to find the a standard error for this, right? A standard error for sample proportion, right? Now, this ME is called margin of error, okay? Margin of error is Z star times this, okay? Z star is a critical value that I will show you how to find it. And confidence interval, okay, is going to be this estimate that we have, plus minus margin of error. So this Z star times this is the margin of error. Confidence interval is, the formulation is quite simple. Confidence interval is the sample statistic, it can be sample proportion or sample mean, plus minus margin of error for that. Okay, that is going to give you confidence interval. Okay, so confidence interval is sample statistic plus minus margin of error, right? Here, margin of error is Z star times the standard error, right? This one is a standard error, right? PQ hat over n, the square root of that. This is a standard error. And multiplied by Z star, that is going to give us margin of error, right? So this is going to give us the confidence interval. And I will show you what is the concept of that. So P hat has a normal distribution, right? This has a normal distribution, and the mean for that is P, the population parameter, and the standard deviation for that is this, right? Now, we don't have the population standard deviation, we don't have the population proportion for failure and success, so we replace them with the sample proportions, right? And we have something like this, and this can be shown by a distribution around this population proportion, okay? And we know that 95% of the data, okay, for this distribution is located between P minus 2 standard deviation, P plus 2 standard deviation. A more precise value for that is 1.96, okay? Now, this is not confidence interval. You can think about it, but this is the confidence interval, and I will explain a more precise explanation of that. So confidence interval for P, for the population proportion, is P hat minus this, P hat minus margin of error, and P hat plus margin of error. This is the confidence interval, okay? Now, when we talk about, you hear this term a lot, 95% confidence interval. What is the meaning of that? And I will explain what the meaning of that is. And for every level of confidence, here, for example, we are talking about 95% confidence interval. For every level of confidence, we have Z star associated with that. And Z star is a critical value associated with that. And I will show you how to find that. But what is this confidence interval? So if you have a sample, this is dependent on the sample that you have, right? This is dependent on the sample that you have, and this is dependent on the sample that you have. So this confidence interval that you calculate is different from sample to sample, right? The confidence interval itself is random. There is randomness in that. When you change your sample, the confidence interval is going to change, right? So what's the meaning of 95% confidence interval? If you say that the probability of the population parameter being in this interval, if you say that there is 95% chance that the population parameter is in this interval, that is wrong. Because in that case, you're talking about just this specific interval. And the population parameter is something that we don't know. That is not random. The population parameter is a specific value, right? If you say that there is 95% chance that the population parameter is in this interval, that is not the correct sentence. Sometimes you're asked, you're given a question, and the question they say you which one of these sentences is correct, right? So you need to be careful about how the wording of the question and how exactly each sentence is, right? So what I just said is not, the meaning of 95% confidence interval. We use this word. We say that this is, for the sample that we have, okay, this is 95% confidence interval. Or we say that we are 95% confident that the population parameter is in this interval. We are 95% confident that the population proportion is in this interval. So we have a sample, we find this interval, like 95% confidence interval, and we say that we are 95% confident that the population parameter is in this interval. And what is the meaning of that? The meaning of that is this. So imagine that the vertical axis here shows the proportion, okay? And this here, this horizontal blue line shows the value for the population parameter, okay? Assume that the population parameter is there, okay? Now, you have a sample. For the sample, you find the confidence interval. You find the interval for the sample. For the first sample, this is the interval that you have. And the population parameter is in this interval. You choose another sample from the population, you find the interval, and the population parameter is in this interval. You keep doing this, and you see that sometimes, once in a while, this interval doesn't include the population parameter. So here, the population parameter is not in the interval. Here, the population parameter is not in the interval, right? But in other cases, the population parameter is in the interval. The concept, the meaning of 95% confidence interval is this. That, for example, if you have 100 different samples from the population, okay? You choose a sample from the population, then again you choose a sample from the population, then again you choose a sample from the population, and imagine that you do that 100 times, okay? If you're talking about 95% confidence interval, that means that 95% of the times, that interval includes the population parameter. That is the meaning of confidence interval. That means that every time you have a sample, you find the interval, and if you do this, for example, 100 times, 95% of the times, that population parameter is going to be in the interval. So if you choose, for example, 20 samples, okay, and if every time that you have a sample from the population, you find this interval, 19 times, which means 95%, is the population parameter is in that interval. Okay, that is the meaning of 95% confidence interval. When we say that we are 95% confident that population parameter is in this interval, this is the meaning of that. That means that if you do sampling and again and you calculate this interval, which depends on the sample that you have, 95% of the times the population parameter is going to be in the interval, right? Is it clear? It's going to be a little bit more clear. So the next point is how to find the z-score, the critical value for z, and I will explain about that. So Now, you can have a deeper understanding about this, that why this concept that I just talked about is valid, but this is something that you need to think about a little bit, and think about central limit theorem and how we used a standard error as an approximation for the standard deviation. Then we got this formulation for confidence interval, and you can figure out where that interpretation that I talked about is coming from, but that requires a little bit thinking, and you can do that. And Z star is associated with the level of confidence, okay? So if, for example, we are interested in 95% confidence, level of confidence, and the Z star is going to be 196, right? Because 196 after mean and 196 before mean, when we have the standard Z distribution, 95% of the data is located there, right? That is how you find Z star. So just for the previous example, we can find the confidence interval, right? We can say, okay, P hat is this, okay? And we can replace the values, and we find this interval. This is P hat Q hat divided by N, right? We find this interval, and this is going to be our 95% confidence interval for the sample that we have, okay? That doesn't mean that there is 95% chance that the population parameter is in this interval. We shouldn't talk about this interval, because when we talk about the concept of confidence interval, we are talking about repeating this process many times, and 95% of the times, the population parameter is going to be in the interval, right? And how do we find the Z score? So this is how we find it. We say, okay, for example, for 90% confidence interval, okay? So when we talk about 90%, 5% of the data is on this side, and 5% of the data is on the left-hand side, okay? So here, the 100% from minus 90% is 10%, right? 5% is on the left-hand side, and 5% is on the right-hand side, okay? Now, if you look at the Z table, okay, and when you look at the Z table, you realize that, for example, let's go to the Z table, you see that for 5%, these two numbers are equally far from 0.05, right? We know how to use the Z table, right? So we are looking for the proportion related to 5% in the Z table, right? Because the tail on the left-hand side was 5%. So we want to find the Z score associated with that. That is going to be the critical value that we have. Okay, and here in the Z table, we see that, okay, these two values, this one is going to be minus 1.645, and this one is going to be minus 1.64. So we find the average for that, and the average, because they're both equally far from 5%, the average for Z is going to be the average for these two Z score associated with this and associated with this, and the average is this, right? So this is for 90%. For 90%, we have this. For 95%, we have this. And for 99%, we have this, right? So this is how you can find Z score. You divide that by 2, and you divide the leftover of the proportion. Like if you're talking about, for example, 70% confidence interval. What is the leftover of that? 30%. So 15% on the left-hand side, 15% on the right-hand side, and you find the associated Z score using the Z table, right? That is going to give you Z star. And when you find Z star, using the formulation that you have, you can easily find margin of error, okay? And you can find the confidence interval, okay? Now, there is one question there is one point that I need to explain, and next time I'm going to discuss hypothesis testing. I think the speed is good, and when we discuss hypothesis testing during the first half of the next lecture, after that, this is the foundation. These are the most important concepts. And everything else that we are going to discuss is easily built on top of these things. So there are going to be the important concepts are central limit theorem, and the concept of confidence interval, the formulation for that, the concept of hypothesis testing, and the formulation for that. Then we see just different versions of them. Like confidence interval for proportion is this. What is confidence interval for mean? It's just, a little bit different, and I will explain about that. So here, there is another point that I want to mention. In general, you want to have a small margin of error, right? Because you want to have a good estimate. You want to, you don't want to have a very large interval and say, I am 100% confidence, and just consider the whole interval and say, I'm 100% confident that the population parameter is in this interval. That is not helpful, right? We want to have a small interval. We are interested in having a small margin of error, but the thing is that the margin of error that we have is dependent on n, right? And is dependent on p hat and q hat, right? So before sampling, we want to have a sample from the population. We don't have p hat, we don't have q hat, we don't have n. How can we find how large the sample should be or need to be for a specific amount of margin of error? Imagine that, and I'm going to finish this in 1 or 2 minutes. So imagine that someone says that I want this margin of error. And it depends on the case. It's different on the study that you're performing. In some cases, a larger margin of error might be OK. You can look at the examples in the textbook in this chapter. In some cases, you're interested in a very small margin of error, OK? Now, you can look at the literature and find an estimate for p hat and q hat, OK? Just look at the literature related to the study that you're performing and find an estimate for p hat and q hat. Put it here. Then this is going to be equal to the margin of error. We have the formulation for the margin of error, z star times this. Then you can find n, right? You can find how large your sample size need to be to have this margin of error, right? So just look at the literature, find the value for p hat and q hat, and that is going to help you with finding the margin of, with using this formulation for finding a right sample size for the margin of error. Now, if there is nothing available in the literature, OK, for p hat and q hat, what is the maximum of this? P hat and q hat are between 0 and 1, and the summation for them is 1. You can show the maximum is when p hat is equal to q hat is equal to half, right? So you can use the maximum value for this, and that is going to give you a larger sample for n. But remember that in some cases, a large sample is going to be quite expensive. So instead of using p hat is equal to q hat is equal to half, you may decide to use the literature to find an estimate for them and find n based on that. Because otherwise, you're going to get a large sample. And in some cases, like when we are talking about election, if I choose a sample of 100 people, I can do that today. I can find people's opinion and then estimate about the population in that day, right? But if my sample is 1 million people, that might take a couple of months. And during that period of time, a lot of things might happen, and the population opinion might change about something. So, and it's going to be quite expensive, right? So you need to look at the resources that you have and make the best decision based on that. Thank you so much, everyone, and I will see you on Tuesday. And I hope that you found this lecture helpful. Tuesday, we are going to discuss hypothesis testing, and we are going to generalize what we discussed to sample mean, and apply the concept of confidence interval for that, and hypothesis testing for both sample mean and sample proportion. Thank you so much, and see you next week.